can...
So, Michael, I enjoyed your lecture, and one of the points I had is that the nanopore technology has been commercialized in the DNA nucleic acid space for such a long time, and it took a long time for someone to figure out to push a protein through the hole. So why is that?
Exactly. Well, a lot of development had to go into that. It took 17 years, like you said. And the major challenges were to slow down the DNA translocation. So initially, free DNA just moves so fast through the nanopores that you cannot resolve the difference in the base pairs. And the very elegant trick that was used was to use a viral packaging motor that grabs onto the DNA and shoves it processively through the pore. It's very elegant.
And so why don't you have that problem with proteins? Because you're not sequencing.
You actually have that problem with proteins as well. This is why we lipid anchor the proteins. We link them to a viscous fluid layer and slow them down.
Excellent.
So how does the presence of the protein actually on that lipid change those processes, that fluidity?
Exactly, that's an interesting question. Yeah. So if you have a lot of protein bound, there can be interactions between the protein, and that could have an influence on the fluidity. We work at very low concentrations, nanomolar and often lower, such that you have very sparse protein that is anchored, and that does not typically change the properties of the lipid membrane. Okay. The protein can move.
And so, a related question would be, so how small can you go? You imagine that the fluid dynamics that you discussed in your lecture apply for single proteins that are in a constrained environment, in fact, are slowed down by the lipid. But is there a case in which the protein is so small, for example, insulin, 6,000 molecular weight, where now you're essentially in a bulk fluid, and you don't see the sidewalls, and you don't have this kind of viscous layer? Can you discuss how that changes the physics?
Yeah, excellent point, excellent point. So the smallest protein that I'm aware of that has been done, not with lipid anchoring, but even free protein translocation, was ubiquitin. And I think it's 14,000. 8,000 or 14,000. I think 8,000 is insulin, 14,000 is ubiquitin, if I remember correctly. But what they took advantage of, this is Amit Meller's group, they took advantage of transient, non-specific absorption. So the ubiquitin molecule absorbs a little bit to the wall of the pore and then desorbs, but it gives them enough time to detect it, and they use very small pores.
Does that mean that you could use something like put a glycocalyx on top of your lipid and then use the glycocalyx protein interaction?
Absolutely.
So you used a heparin or something and you get the binding
that's
that way.
That's a very good idea. If you wanted that specific interaction, you could use it.
You could use more of a biomimetic approach rather than, and that might allow you to look at a whole other range of molecules.
It's a very good point. We've done exactly this experiment with cholera toxin. Cholera toxin binds to sugar residues and lipids. We've done exactly this. It binds, it assembles, we can translocate it, we get the right volume.
Yeah.
So I was going to say, she stole my question, but
I've been doing that for years.
If you put the opposite stereoisomer of a phospholipid, so the non-natural form, and then you put phospholipase, which is 14,000 molecular weight, and allow the whole thing to jump and hop because it has this mechanism of catalytic hopping across, but because it can't hydrolyze the substrate, you would then have an inert system where it would bounce along and be confused, and you can compare it to the system which you present with its natural lipid.
Correct, which we've done. We've done that experiment.
Excellent.
So I didn't know about the hopping on the unnatural one. That's very interesting. But we've done the natural one, and then of course it processively works on these lipids.
That's correct.
And if you work in very low ionic strength, you can measure the resistance to the pore. And then what happens as it cleaves head groups, the lipids that are initially switterionic become charged, and then they bind electrolyte and reduce the resistance. And you get charge carriers concentrated in the pore because of the charge on the wall, and it reduces. And you can follow it. You can do enzyme kinetics. We've done this.
Well,
but we haven't done the other thing.
Fascinating to listen to your lecture.
Yeah.
Congratulations.
Thank you.
Thanks
so much.
for your interest.
It's been great.